In this video, I'm going to show you how to use the tangent function property in graphing to create the tangent to a function at a given specific point. So just some prior knowledge. The tangent to a function is basically the equation of a line, or it's a line that is touching a function at a given specific point, and you can change that point. So there's many tangents to a given function. The first derivative of a function is an equation that helps you determine the slope of a tangent at any given point. So again, each derivative, if you plug in the point value for a variable, you're going to find the slope of the tangent at that point. And we'll talk about this in a minute. And then point slope form is some prior knowledge that once I can find the slope of a given tangent point, I can create the tangent, the function for that, using my point slope form. So I'm going to kind of walk through all that and how Classpad.net helps students visualize this is a process that they're going through. We tend to teach them the process, and I'm going to show you how Classpad allows you to actually visualize and understand and make the connections. So let's pull up a graph. So here's a graph, and the first thing is let's put a function in there. So I'm going to put in a function, so a curve, and let's make it not super easy, but oops. All right, so here's a function. So it's going to graph the function. So here's our function. Now, if I want students to calculate the derivative and all that, which I'm going to do, but I want them to understand this process. How is the tangent line connected to the derivative of the function, and where is that equation for the tangent coming from? I don't want to just give them the process. I want them to kind of try to figure it out on their own. So this is what I'm trying to show you is, here's my function. If I click my function, notice it gets highlighted. It brings up some key points here, which we're not going to focus on right now because what we're interested in is the tangent. So when you click on that, this little icon right here pops up and becomes available, and this is called the property. And you'll notice that when you click it, you can do three different things. You can find the tangent to the function at a specific point. You can do the normal line, which we're going to do in another video, or the integral. So let's click tangent and see what happens. And the program itself picks an arbitrary point that's on this function. So you know that this is a point on the function, and also it's the tangent, because it's showing that it's connected to both the line, the tangent line, and the original function. And what this means is this line is tangent to the blue function because it's touching the blue function at that specific point in time. And the slope at this specific point on the function is where the derivative comes from. So this slope of 2.86 is coming from the derivative of the original function. So for students, we've taught them the process of finding the derivative. So I'm going to pull up a text sticky here. And what I want is, now how am I making this connection to this original function and this slope? How is that connected? And we tell students that the slope of this tangent at that specific point, so at the value x 1.3, this is the slope. Where did that come from? Well, it comes from the derivative, which we've given them a definition. The first derivative of a function is the equation that lets you determine the slope of a line at a specific point. So the tangent, this tangent line at this specific point, 1.3, x equals 1.3, has a slope of 2.87 in that particular instant. Where did that come from? So now you can pull up and let's find the derivative, and I'm going to use the power rules. So 3 times 1, x, so I get 3. The derivative is y equals 3x squared. And I'm using math type right now in the text sticky. Minus 2 times 2 is 4x, and I don't have power, plus 1 times 3 is 3. So this is the derivative. And so what we're trying to tell students, or help students understand, is this slope of this tangent line at that value of 1.3 is determined by plugging in that value of x into the derivative. So let's pull up a calculate sticky and actually do that. So here's my derivative equation that I'm going to plug in, the value of this x value at 1.3. So let's evaluate this derivative, the first derivative, at that value of x, and I should get 2.87. Let's see if we do. And I'm going to pull this up here so I can see it. So I'm doing 3 times, what did we say, 1.03. That was that value, I think. Make sure I'm doing that right. Yep, 1.30. So I'm using the current value, so 1.3, raised, and I'm plugging it into the first derivative because I'm just verifying that I should be getting this slope, right? So then minus 4 times 1.3. Again, I'm just evaluating at that given value of x, the first derivative. And when I hit enter, 2.87. Okay, so that makes sense. So what happens if I were to move, and this is the beauty of dynamic math, you can move this point, and let's just verify that it happens again. So let's move it down here this time. All right, so notice it's a different tangent because I'm at a different value of x on the function. So this is now the tangent line at that value of x. Notice my equation of the tangent changed. It has a different slope. So let's just verify again. The derivative didn't change. What's changed is the value I'm inputting for my derivative x. And this time I'm inputting a negative 0.5. And instead of typing it over, I'm just going to change my original to be negative 0.5. Anytime I plugged in negative 0.5, hit enter, and I get 5.75. So they could do this several times and really kind of verify, oh, okay, so that makes sense. The slope of the tangent is where I'm taking the value of the function at a specific x value and plugging it into my first derivative. That's where the slope's coming from. Well, where is this? Notice that the equation's in y slope-intercept form. Where's this 0.75 coming from? Well, it's coming from two things. I know the slope's coming from my evaluating the first derivative at that given value of x. Where's this 0.75 coming from? Well, notice this given value of x, if I'm at x, this point, this tangent point, is on both the tangent line and also the function. So this given value of x gives me a value for the original function, a y value of negative 2.3. And if I wanted to verify that, what happens if I plug in this given value of x to the original function? So let's just do that. So we have negative 0.5 cubed. Oops, I didn't need to do that. And all I'm doing is plugging into the original function. So 2 times negative 0.5 squared plus 3 times negative 0.5, right? Oh, I forgot the negative, negative 0.5. Oh, I must have done something wrong here. Negative 0.5 cubed minus 2 plus. All right, I plugged this in wrong, so I went back and redid it. So basically, I'm taking this given value of x and plugging back into the original equation, and that's where this negative 2.13, they rounded obviously, came from. So this point is then going to help me figure out the equation of the tangent, because what do I now have? I have a slope, which we already know is 5.75 because we figured that out here. And using the derivative, you plug in the value of x to the derivative, the first derivative, that gives you the slope of the tangent line. And then I know I have a y coordinate, a point on that tangent line is the given x and the given y, which came from the original equation, so we were just verifying that. So now I use my point slope form. So what's my point slope form say? My point slope form says this red line, this tangent line, has a slope and it has a point at negative 0.5 negative 2.3. So y minus the y coordinates, which in this case is negative 2.13. I'm just using my slope-intercept, point slope form, sorry, equals the slope that we already figured out was 5.75. So 5.75 times x minus the x value at that tangent point. So this is the equation of the line. We have obviously worked it out and evaluated and changed it to the slope-intercept form, but it starts out as this: the slope that we determined from the first derivative, and then the point, the x and y coordinates of the point that happens to be on both the tangent at that point and the function at that point, at that x value. I just plug it into the point slope form. So this is just prior knowledge at this point. And when I do the calculations on this, so what am I going to do? I'm going to multiply 5.75 by x and by, and if we need to, we can use our calculator. So 5.75 times a negative, and I'll just put this in parentheses, negative 0.5. That gives me 2.875. So now what's my equation? I'm just going to go down to my next line here. I have y, let's change this to, because two negatives make equals 5.75 x plus 2.875. So right now, all we're doing is algebraic manipulation, right? We're just changing one form of the equation to its an equivalent form. So from point slope form to slope intercept form. And so now I'm going to subtract 2.13 from both sides. So let's just do that. 2.13 from both sides. And that gives me 0.745, or rounded 0.75. So that's where that number's coming from. So really, I just have to know how to find the derivative, and that derivative gives me this slope number here. And at this specific point in time, I have a point that's on both the tangent and on the function, and I can find that coordinate, that y coordinate, simply by plugging in that x value into the original function. So I'm basically plugging in the original into both the derivative to get the slope and the original to get my y coordinate. And once I have my y coordinate, I just write the point slope form. And then if I want it in slope intercept form, I can easily do that by algebraic manipulation. So this visual helps me understand, and I can then practice and move things. So now let's see, can we figure it out again if we change the point to something different? Let's make it be 2. Let's make it be kind of easy, right? So notice how the tangent has changed, the slope has changed, my coordinate has changed, my coordinate points have changed, my x input now is 2, and the y output for the original function and also on this tangent line. So this coordinate is on both, so that's why I can use it in both. And now I can verify again. How do I find the slope, this 7? Where'd that come from? Well, plug this 2 value into, which is the point of tangency, into the derivative to verify. So 3, and let's just do this, 2 squared is 4. So 12 minus 8 is 4. 4 plus 3 is 7. So there's where my 7 comes from. So as you really try to help students understand these definitions that we give them, bring in the visual.